Okay, section 3.5, shallow autoencoders. So far in this chapter, we explored logistic and multinomial regression. Both of these models are shallow neural networks which do not involve hidden layers for supervised learning where the data is labeled. There are special cases of deep learning models. The same goes for the linear regression model of section 2.3, that's in the previous chapter. It was made evident that linear regression is also a deep learning model, actually in section 3.2 of this chapter. Thus, the key supervised learning models that we discussed up until this point, all of which are simple neural networks, fall under the umbrella of deep learning. We now devote this last section of the chapter to simple neural networks that are used for unsupervised learning, where the unlabeled data is of the form, data is just a sequence of vectors, x1 through xn. Namely, we introduce autoencoder architectures and focus primarily on shallow versions of these architectures. In section 2.1, we overviewed the concept of unsupervised learning in the context of machine learning activities. And in section 2.6, we surveyed basic unsupervised learning techniques, including principal component analysis, that's PCA. As we see in the current section, PCA can be cast as a special case of an autoencoder, and this positions PCA as a form of simple neural network-based learning as well. Let's do it. Autoencoder principles. Before we explore several varied applications of autoencoders, let us focus on their basic architecture. Consider figure 311, which presents a schematic of an autoencoder with a single hidden layer. The input, a vector x in RP, is transformed into what we call a bottleneck, also called the code, which is some vector x tilde in Rm, and is the hidden layer of the model. Then the bottleneck is further transformed into the output, x hat, which is again in Rp, the dimension p. Okay, so we go from dimension p to dimension m, and then back to dimension p. The part of the encoder that transforms the input into the bottleneck is called the encoder. And the part of the autoencoder that transforms the bottleneck to the output is called the decoder. So you've got your encoder here and your decoder here. Okay, that's it. Both the encoder and the decoder have parameters that are to be learned. Note that many other deep learning models in this book will also have hidden layers. In fact, representing and computing gradients for parameters of such layers is the focus of Chapter 5 and stands at the heart of deep learning. In the autoencoder example, the single hidden layer is also the bottleneck of the autoencoder, and thus we informally consider this shallow autoencoder as simple. Other deeper autoencoders may have multiple hidden layers, of which one should be treated as a bottleneck or code. Interestingly, for input x, once parameters are trained, we generally expect the autoencoder to generate output x hat that is as similar to the input x as possible. This property of autoencoders, after which they are named, may first seem obscure, since it means that the autoencoder is a form of an identity function. However, this architecture is actually very useful for a variety of applications, some of which are detailed in this section, and others appearing as parts of more complicated models, as for example, sequence models, which we discuss in Chapter 7. For now, as the most basic application, consider the activity of data reduction already surveyed in section 2.6, previous chapter, in the context of PCA, principal component analysis, and SVD, singular value decomposition. For this, assume that the dimension of the bottleneck M is significantly smaller than the input and output dimension P. In other non-data reduction applications, we may also have that m is greater or equal than p. For example, return to the mnist digits initially introduced in section 1.4. So remember, each digit is 28 by 28 pixels. And 28 by 28 means that p equals 748. That's 28 squared. For our example here, assume we have an autoencoder with m equals 30. If indeed a trained autoencoder yields that the input x is approximately equal to the output x tilde, then it means that we have an immediate data reduction method. With a trained encoder, we are able to convert digit images, each of size 784, into much smaller vectors, each of size 30. With a trained decoder, we're able to convert back and get an approximation of the original image. This choice of m implies a rather remarkable compression factor of about 26, so 784 divided by 30. Figure 312 presents a compression-decompression effect of several types of autoencoders with m equals 30. The first row presents the untouched images, mnist images. The second row presents the effect of reducing the images via PCA, principal component analysis, which we call in this section a shallow linear autoencoder, and then reverting back to the image. So that's what PCA does. The third row presents the effect of a shallow nonlinear autoencoder. Finally, the last row presents the effect with a richer autoencoder that has several hidden layers. Okay. There are multiple other applications of autoencoders which we see in survey. However, let us first formulate these types of models more precisely. Single layer autoencoders. As already mentioned above, we may view an autoencoder as a function parameterized by theta, f theta, from Rp to Rp, where theta are the trainable parameters of this function. These parameters theta are ideally influence a function's operation such that we have that f theta of some x star is approximately x star, where x star is an arbitrary observation from either the seen or the unseen data. The approximate inequality can be considered informally as closeness of two vectors. In practice, when faced with training data x1 through xn, we train the autoencoder, which means learn the parameters theta, such that a loss c theta given the data, and this is the same expression for the loss we've always had, is minimized. This is a similar loss function setup to that used in supervised contexts such as linear regression, logistic regression, multinomial regression, or the deep learning models that are in the chapters that follow. For autoencoders, we construct the loss for an individual observation, Ci, as some distance penalty measure between the input observation Xi and the output X hat I. Okay, so X hat I is the output we'd get for the given theta. Contrast this with supervised learning, where we compared the observed label and the predicted label. That is, with autoencoders, the target of the model is the input in contrast to a label yi in supervised learning. The most straightforward choice for the distance penalty in Ci, so Ci is a cost function for individual observation, is the square of the Euclidean distance. Namely, Ci theta would be Xi minus the autoencoder applied on Xi squared, okay, norm squared. And thus, this is the total cost. Okay, so that's like a mean square error cost. With this cost structure, learning the parameters theta of an autoencoder based on data D is a process of minimizing this guy, the cost. That's obvious. In general, autoencoders may have architectures similar to the fully connected deep neural networks that we studied in Chapter 5, as well as extensions in the chapters that follow. This may include multiple hidden layers, convolutional layers, and other constructs. At this point, to understand the key concepts, let us revert to figure 311 and consider autoencoders composed of the same components of that figure. So here's figure 311, and we're just going to have exactly the components here. We'll basically have a transformation from the input to the bottleneck and a transformation from the bottleneck to the output. And these transformations are respectively called encoder and decoder. Specifically, we decompose f theta to be a composition of the encoder function denoted via f theta 1, 1, and the decoder function denoted by f theta 2, 2, where theta 1 are the parameters of the encoder and theta 2 are the parameters of the decoder. Let's give these different colors. So we've got this, and we've got the parameters of the encoder, and we've got the parameters of the decoder. That is the output, which we get, the output x hat, which is f theta applied to x, is the composition of the decoder applied on the encoder, and that is applied on the input x. Okay. Or the notation using the square bracketed superscript for the functions and parameters is in agreement with the notation we use for layers of deep neural networks in chapters 5 and onwards. This will come in the sequel. Okay. So all we have is we have these two separate functions, f theta 1 and f theta 2. In general, one may construct all kinds of structures for the encoder, decoder, and their parameters. In our case, we consider a specific single layer neural network structure. So we define f theta 1 as S1 applied to B1 plus W1U. So we have an affine transformation here. And we'll say what S1 is in a second. It's an activation function. And similarly, sorry, I'm using now different colors than what was before. And we have the same type of construction for the decoder. Okay, so not much happening here. Where the notation is somewhat similar to 326, which was before. Specifically for L equals 1, 2, B superscript L are vectors, and W superscript L are matrices. And SL are vector activation functions. So it's a function from Rm to Rm, and S2 is from Rp to Rp. Before describing the exact details of these functions, let us focus on the autoencoder parameters. The encoder parameters theta 1 are composed of the bias B1. So let's actually see this here. We'll mark it as we read. So the bias B1 is a vector in Rm. And a weight matrix W1, which is a M by P matrix. So it converts a U input, which is P-dimensional, into M-dimensional. Okay. And the decoder parameters theta 2 are composed of the bias B2. Okay. And the weight matrix W2, so bias B2 is P-dimensional, and this is the transpose dimension in a sense, W2, because it converts you from M to P. Thus, a complete list of parameters for the autoencoder are these two bias vectors and these two weight matrices. That's all there is to it here. Returning to the vector activation functions S1 and S2, we construct these based on scalar activation functions. So we have some scalar activation functions, sigma L. So each function, scalar activation is an R2R function, such as, for example, the sigmoid function, which we already saw, or if you want to go simpler, even the identity function, or one of the many other variants where there's a whole section devoted to them, and that's section 5.3 in the sequel. Specifically, we'll let SLZ be the element-wise application of the scalar activation sigma L on each coordinate of Z, namely, when you write something like this, you mean that you apply the scalar activation function on each of the coordinates. That's all there is to it. The choice of the type of scalar activation functions may depend on the domain of the input X, since the output of the model aims to reconstruct the input. For example, use a sigmoid function for sigma 2, that's for the decoder, of the use of the sigmoid for sigma 2 restricts the output to be in the range 0, 1, and this will clearly be unstable in cases where the input is not limited to that range, right? So with this notation in place, it may also be useful to see the individual representation of the bottleneck units, x1 to xn. So the bottleneck units, again, are these guys here. Okay, so we can just write an expression for each of these guys in there if we would like. And xi, that's in the bottleneck units. And I think here we have a typo. This should be a tilde and this should be a hat. So we'll fix that. Okay. So xi is the bi1 plus the application of the matrix multiplication on the input, and we apply to this input activation. So that was the encoder, and then this here is the decoder. This set of equations is the first non-shallow single hidden layer neural network which we see in this book. Note also that we often use a notation AI to be xi hat, as it is activation of a unit or neuron within the encoder. Okay, maybe let's see that I got this correct. So the hats, hats we use for the output and tildes for the bottleneck. Okay. Also, it may be useful to see the loss function representation as, and now we can take all of what we've had and we can say, well, the loss function representation is now going to be the average of the sum of the individual loss functions. And each individual loss function is a norm squared. Norm squared of what? Of the difference between the input and the application of the autoencoder. And the application of the autoencoder is the composition of the encoder inside the decoder. That's what we've got here. Okay, sorry. So that's all of that. With this loss function, for given data D, the learned autoencoder parameters theta hat are given by the solution to the optimization problem. Let's minimize this guy. Okay, so we minimize this guy, and that's how we learn the parameters. Okay, a lot of details so far. Now here's a claim. PCA, that's principal component analysis, PCA is an autoencoder. It turns out that autoencoders, generalized principal component analysis, PCA, introduced in section 2.6. That's in the previous chapter, in chapter 2. We overview the details by seeing that PCA is essentially a shallow autoencoder with identity activation functions. Okay, so this is identity activation functions for L equals 1, 2, also known as a linear autoencoder. Specifically, we now summarize how PCA yields one possible solution to the learning optimization problem for linear autoencoders. Note that some of the mathematical details below, this is an important comment because I'm going to really fly through this, and it's hard to get this on a first listen of a video, but have a read if you're really interested in this. This is a subtle issue. Note that some of the mathematical details below may be skipped on a first reading without loss of continuity. The key outcome of this subsection is that PCA and linear autoencoders are essentially the same. So you know what? I'll actually get back to this section that shows that PCA is a linear autoencoder at the end of the video. We'll treat it as an appendix to the video, because this is really of higher detail than most of the other things that we have, and it's actually not as important for a first understanding. So we'll get back to this soon. So the next bit. Autoencoders is a form of nonlinear PCA. So all we did above, what we just skipped is mathematical details showing that autoencoders are generalizations of PCA, really. So PCA is like an autoencoder when you don't have a nonlinear activation function. When your activation function is just identity, so all you have is linear operators. But now we say autoencoders is a form of nonlinear PCA. As we discussed above, encoding and decoding with PCA projects the p-dimensional feature vector X onto an m-dimensional subspace. When p equals 2, so say you have two features and m equals 1, this can be viewed as a projection of points from a plane, from p equals 2, onto a line. When p equals 3 and m equals 2, this is a projection of points from three-dimension space onto some plane. And similarly, in more realistic higher dimensions of p, we project onto a linear subspace of dimension m. As such, the bottleneck of the linear encoder PCA encodes the location of the points on the projected space. Linear subspace projection is sometimes a sufficient data reduction technique, and at other times is not. In such cases, there are other forms of nonlinear PCA, where points are projected onto manifolds that are generally curved. Since autoencoders generalize PCA, they present us with one such rich class of nonlinear PCA models. As an illustration, consider figure 313. So figure 313, where we consider synthetic data with p equals 2, which we wish to encode with m equals 1. This means that the bottleneck layer or their code represents a value on the real line for each data point. Okay, so let's pause for a second and just read. So what we have here is we synthetically created this collection of points. So you see here, okay, obviously fall according to some pattern, all right? And they live in the x1, x2 plane. So p equals 2. Okay, that's p equals 2. Right? Now, we can do PCA encoding, or we can do some nonlinear encoding. In both cases, we project into dimension m equals 1. All right? And in both cases, you just have each point is mapped onto a point, and here each point is mapped onto a point. So they're mapped onto the real line. That is the encoder. Now, when we do decoding, when we do PCA decoding, then we're actually going to put things back on a hyperplane because it was all linear, so it was one line. But when we do nonlinear decoding, we're going to put it on a manifold. Okay, which in this case, a manifold kind of matches the desired shape. So let's read more. This means that the bottleneck near the code represents a value on the real line for each data point. If we use PCA, which is in red, then this encoding translates to a location on the linear subspace of R2. However, so the linear subspace is this line, okay, or hyperplane. However, if we modify the identity activation functions in autoencoder to be nonlinear, in blue, then the projection is on a manifold which is generally curved. In this example, the nonlinear activation functions are taken as tanh functions. See also section 5.3 where we speak about activation functions. So this is a very schematic illustration where we just take from p equals 2 to m equals 1 and then back to p equals 2. And, you know, it works well for this type of data, which is actually not so different in shape to the tanh activation function. So it unsurprisingly works well. But the point is that we can actually project onto a lower dimension, and then we project back. And with the nonlinear autoencoder, with the general autoencoder, you project back onto something that is curved. Now, as a further illustration, a more realistic one, consider using an autoencoder on MNIST, where P is 28 by 28 or 784, and we use M equal 2. We encode this via PCA or a shallow nonlinear autoencoder and a deep autoencoder that has hidden layers. In figure 3.14, we present scatter plots of the codes for various types of autoencoders for both the training and testing sets. That is, the autoencoders are trained on the training set, and the codes presented are both for the training set and for the testing set data. While the training and testing does not directly involve the labels, the digits 0 to 9, in our visualization, we color code points based on the labels. So we have no notion of what the labels, but when we reshow, we actually show what the labels are. This allows us to see how different labels are generally encoded onto different regions of the code space. Recall also figure 2.14b, which is of a similar nature. Okay, in chapter 2, we had a figure of this nature, I think, on the Wisconsin breast cancer data set. Okay, so what we see in here is autoencoders applies to MNIST, so A to C are from the training set and D to F are for the test set. Okay, in the first column we use, so this is PCA. Okay, and in the middle column we use a shallow autoencoder or a simple autoencoder, similar to what we're speaking about here. Last column we use a deep autoencoder. We really haven't spoken about deep yet. But what we see is that the more complex autoencoder, for example, the deep autoencoder allows us to really have it, and then we paint the points according to the labels 0 to 9, okay, with different colors. We see a nice separation here with this autoencoder, with the deep autoencoder, and even some separation with the shallow one. Okay. Keeping in mind that one application of such data reduction is to help separate the data, it is evident that as model complexity increases, moving right along the displays of the figure, somewhat better separation occurs in the data. In particular, compare D based on the test set using PCA, okay, and F based on the test set using the deep autoencoder, like we just said. Refer also to figure 3.12, which illustrates the reconstruction effect for various types of autoencoders. Here M equals 30. So figure 3.12 was, again, this figure of reconstructing with various autoencoders. Here we're actually seeing what happens to the images themselves as we reconstruct. So both views are interesting. In terms of reconstructions, it is also evident in this case that more complex models exhibit better reconstruction abilities. Okay, so now let's speak about applications and architectures. We've already seen the archetypical autoencoder application, namely data reduction. Yet there are many more applications and associated architectures of autoencoders. We now discuss some of these. We first consider various ways in which data reduction can be employed to help with additional machine learning activities. We then discuss denoising, which is a different application to data reduction. We close with ways in which interpolation in the latent space of the bottleneck are useful. The discussion here is just a brief summary, and more information is suggested in the notes and references at the end of the chapter. In terms of uses of data reduction, let us consider both supervised and unsupervised learning. In the supervised setting, whenever a data set D, so data set composed of pairs of features and labels, X's and Y's, is used, where the dimension of Xi is P, one may attempt to reduce the dimension of the input features to M less than P and obtain a data set, call it D tilde, which has X tildes, okay, and there with reduced dimension. With such a data set, training a supervised learning model to predict Y in terms of X tilde in RM may sometimes yield much better performance than using the original X in RP. This process requires training an autoencoder as well as training the model. Then in production, with unseen data, for any X star, we first use the trained encoder to obtain X star tilde. We then use a trained model on X star tilde to obtain Y hat. Note that with such an activity, we do not use the decoder per se. To take this application of data reduction even further, consider a situation with yi, which is in RQ, where Q is not small. So now the labels are not scalars, but are rather Q-dimensional vectors. So high-dimensional labels such as segmentation maps on images, for example. In this case, one may encode both the feature vector and the label, each with their own autoencoder, to obtain encoded data of the form D tilde, which has X tildes and Y tildes. Say with Xi in RMP and Yi in RMQ, with MP less than P and MQ less than Q. One may then train a supervised model using this D tilde data. Such a model predicts Y tilde hat star in RMQ for each encoded feature X star in RMP. With this setup, when the model is used in production, one first observes a feature vector X star, then uses a feature vector encoder to create X star tilde, then uses a model to predict Y star tilde hat, and finally uses the label decoder to obtain Y star hat. Hence, with such an activity in production, the encoder of the feature vector and the decoder of the label are used. Okay, so it's basically using an autoencoder as part of a supervised model. In terms of unsupervised learning, there are many secondary ways to use applications of autoencoder-based data reduction as well. As one example, assume that we wish to cluster images. A naive approach may be to treat each image as a vector and then use an algorithm such as k-means, see section 2.6, to cluster the vector. This approach has many drawbacks since the distance between images is based on exact location, indices of pixels within an image. For example, two images of the same object with slightly different camera locations would be generally far when comparing the Euclidean distance between the associated vectors. A more suitable approach is to use an autoencoder for data reduction of the image to a low dimension and then to perform clustering on the reduced dimensional codes. See, for example, figure 3.14f. Here, so we'll go soon to 314f. Okay, so look at 314f, right? So we can cluster, for example, digits. Okay, we can cluster all of the digits of a different group very easily, right? You see that there's quite a good separation in the code space. Here, m equals 2, and with such an encoding, clustering the vectors on the two-dimensional code space will generally work well. We now move away from data reduction and consider an architecture called the denoising autoencoder, which is illustrated in figure 315. This model learns to remove noise during the reconstruction step for noisy input data. It takes in partially corrupted inputs and learns to recover the original denoised input. It relies on the hypothesis that high-level representations are relatively stable and robust to entry corruption, and that the model is able to extract characteristics that are useful for the representation of the input distribution. In terms of architectures, denoising autoencoders exhibit a similar architecture to the usual autoencoder, as they involve an encoder F1 theta sub theta 1 and a decoder F2 say sub theta 2. However, a key difference is that during the learning process, it is trained on noisy samples and the loss function is modified. First, the initial input X is corrupted into, say, this X brev via some predefined stochastic mapping, performing a partial destruction. In practice, the main corruption mapping include adding Gaussian noise or masking noise, a fraction of the input chosen at random, for example, forced to 0, or salt and pepper noise, a fraction of the input chosen at random for each example set to its minimum maximum value with uniform probability. Now, with the corrupted input xbrev, the autoencoder encodes and decodes xbrev in the usual way, yielding a reconstructed xbrev hat. Okay, so you apply the encoder and the decoder to get xbrev hat. However, instead of using loss like equation 3.36, that's a basic loss we had for autoencoder, which would compare xbrev and xbrev hat, we modify the loss function for observation I to be Ci, which compares xbrev hat I and the non-denoised Xi. Hence, during training, we seek parameters theta that try to remove the noise as much as possible. When used in production on an unseen data sample, X star, the data corruption step is clearly not employed. Instead, at this point, the autoencoder output, F theta X star, is conditioned to generate outputs X hat star that are denoised. That's pretty cool, a denoising autoencoder. Let's look again at the figure. So for denoising, so we've got original data. Okay, and then we do some partial destruction of the data. So here's some partial destruction of the data. And we train comparing the original data and the reconstructed input. And in production system, that's what we have in the dotted line. In the production system like this, then what we have is we get some destructed input, but it will ideally denoise and give us denoised data. And that often works well. As a third general application of autoencoders, let us consider interpolation on the latent space. And this is a big idea, takes xi and xj from the data, and with data is x1 through xn, and consider the convex combination lambda xi plus 1 minus lambda xj, and call that x lambda naive for some lambda in 0, 1. Okay, so just pick some scalar 0, 1 and do a convex combination of the two vectors on two data points. Ideally, such an x lambda naive may serve as a weighted average between the two observations, where lambda clearly captures which observation has more weight. However, with most data, such arithmetic on the associated feature vectors is too naive and often meaningless for similar reasons to those discussed above in the context of k-means clustering of image. For example, in figure 3.6a, we see such an interpolation with lambda half. So let's go to figure 3.6a. Oh, sorry, there's no a here, but this is the a. Okay, so we have xi is this digit of 3 and xj is this digit of 3. So if you do a naive interpolation, of course, you're just doing some superposition of those two images. That's not really interpolating these two digits. Okay. When considering the latent space, representation of the images. So if you now go to the latent space, it is often possible to create a much more meaningful interpolation between the images. To do so, we train an autoencoder and then encode xi and xj to obtain xi tilde and xj tilde, their values in the latent space. We then interpolate on the codes and finally decode x tilde lambda to obtain the interpolated images. That is, using the notation of 337 in the equation we had above, omitting parameter subscripts, we have, so this is what we do. So we apply the encoder to xi, we apply the encoder to xj, and we do their convex combination. So this in blue here is a convex combination of the latent space. Then we apply the decoder to the whole thing. So we get x lambda encoder. So we did the interpolation inside the latent space. In figure 316b, we'll see that in a second, we see such an interpolation. This property of latent space representations is also discussed in chapter 8 in the context of general adversarial networks GANs, where applications of such interpolations are further discussed. At this point, let us mention that one potential application of such interpolation is for design purposes, say in art or architecture, when one chooses two samples as a starting point and then uses interpolation to see other samples lying in between. Other applications of data augmentation are also discussed in the sequel. Okay, so let's just look at the interpolation. So when we do when we convert this 3 and this 3 to latent space, do an interpolation in latent space, and then encode back, we actually get something which averaged these two images a bit better. Okay, this is a very simplistic example with a simple autoencoder on MNIST. Okay, so this concludes this section and chapter. That was a section on autoencoders. We still have the debt of reading this bit on the PCAs and autoencoder. So these were mathematical details dealing with PCAs and autoencoder. And here's a description, and we won't read it in this video, but have a look at the details. This is actually quite dense and in a sense falls when we say that it can be skipped the first reading, but it is an overview of how PCA can be represented as a shallow autoencoder with linear activation functions. So you can read that yourself if you're interested. And as always, thank you. Please leave any comments at the bottom of the video if you found this interesting or if you have any other thoughts. And that's chapter 3. Thank you. Bye-bye.